hopefully the last video didn't scare you too terribly bad. A lot of what I did in the last video was to sort of show you where that constraint comes from, why we have that constraint in this particular model, and what it means. Now, will you be expected to formulate that on your own? No. Will you be expected to convert it from nominal to real? Probably. That's my guess. Could be wrong, but my guess is, oh, my computer gave me a nice little notification. Thanks, computer. Maybe, maybe not. I don't know yet. But we had our, sorry, I got distracted for a second, my mistake. So we had the nominal budget constraint, we converted it to real, right? So what we currently have now are a couple of things. One, you need for me to check my phone, so I just got an email, and it is okay. So what we had, utility was pretty close to what we saw with that first model. Still have the infinite horizon, still have the exponential discounting. Like this, but instead of it just being in terms of consumption, well, it's also in terms of real money balances. So utility increases as the amount of our real money balances goes up. Right, so if you got 20 bucks in your wallet, and then you get 30 bucks in your wallet, well, if it's nominal $20, $30, right, utility will probably increase, but we need to be able to control for the rate of inflation, right? So if you go from $20 in your wallet to, say, $25 in your wallet in real terms, right, that's how much your utility would actually increase, because it's not a function of nominal money balances, it's a function of real money balances. Hence why we had to convert the constraint from nominal to real, because we needed to have real money balances inside the constraint in order to be able to do stuff with this utility function. So let's write out the constraint. Now the constraint was quite a bit longer than what we saw before, because now we also had the flow of money, we had the flow of bonds, and we had transfers net of taxes. So the constraint remember, on this side, we have the source of funds. All right, so this whole side of the constraint is the source of funds. This side is the use of funds. We can either consume gain more real money balances, get more bonds, or purchase more capital. Right, so in this case, the source of funds is equal to the use of funds. But remember, this constraint in the way that it's currently setting isn't really the most useful if we're going to do that nice little dynamic programming thing that really simplifies down all the amount of work that we got to do. Right, what do we have to do? We got to solve this guy for CT. So to solve this constraint for CT, just subtract everything from this side over to this side. at this. So I get CT equals AT times KT to the alpha, right? Production. Plus today's real money balances minus tomorrow's real money balances, but we're adjusting for inflation, right? Otherwise it would just be nominal money balances. Plus bonds that we have today minus bonds that we can pay tomorrow. Right, so everything that is positive here, we see, is stuff that can increase consumption. Everything that's negative is stuff that decreases consumption. Right, the stuff that decreases consumption, in this case, is stuff that we could spend alternatively to consumption. Right, because we can't just consume all that we want, get all the capital we want, get all the bonds and all the money holdings that we want. No, we can't do that. What we can do, however, is split up what we're bringing in, right? Because the source of funds is what we're bringing in. This is like our income. The use of funds is how we spend that income. So if I'm consuming, right, the more I consume, the less real money balances I can get for tomorrow, and the fewer bonds I can buy, and the less capital I can buy, the less I can invest. Right? Therefore, everything that's negative in this constraint is stuff that would prevent me from consuming things. Now, what I do here, once I have this constraint solved in terms of C, well then I take that and I plug it in right here, and I formulate my Bellman equation. So, I'll set the Bellman equation up. Now, it's no longer just V of only KT. Right? There are other things that I can get as well. Namely, two other things that I can get. What are those two other things that I can get? I'll let you look at this for a minute and think about the two things that I can choose to get instead of consumption and are in this model that were not in the neoclassical business cycle model or the dynamic general equilibrium model that you saw before. Right, what are those things? Well, one of them is bonds, right? Because we can either consume and buy capital or invest. We could buy bonds. Or the other thing would be money. So it's now a function of capital, money, and bonds. KT, MT, and BT. Right, now when I set up this Bellman equation, I'm going to do the natural log of consumption, which is equal to all this stuff here. Now, I will let it be said, theoretically you could just do natural log of C plus theta times natural log of M plus, beta times V of KT plus 1, MT plus 1, BT plus 1. As long as you understand that you have to do the chain rule on all of these derivatives. So what I am going to do is for writing the Bellman equation, I am going to write out this entire constraint inside. Like this. I'm going to close these parentheses out. Right, so natural log of consumption, everything that's purple here, is equal to consumption. But now I've also got theta times the natural log of m. Now don't worry about this. You don't have to do anything with substituting anything in for m here. You don't have to do it. Don't worry about it. So I just do plus theta mt, or theta ln of mt. And then I close my giant brackets. So I get that. Looks like a lot. I mean, yeah, it kind of is a lot, but it's really not that bad. Then I do plus beta times v of, well, these three things just updated one period. kt plus 1, nt plus 1, bt plus 1. Like that. This is my Bellman equation for the money in the utility function model. And you're probably cursing me to death right now because of that really, really long constraint. But don't worry, because you will get the constraint. Like in homework, exams, etc., you will have that constraint. You have nothing to worry about there. So, now that we have this, what we need to do is we need to get some derivatives. So in fact, what I'm going to do, I'm going to erase all this stuff, and I am going to rewrite this Bellman equation up top. Okay, now that's done. Now we can move on. Okay, so we have to take three derivatives. We need three first order conditions. And it may look like a lot. But I mean, ultimately what we're doing isn't too terribly different from what we did with that first general equilibrium model, except, well, we just have a couple more derivatives that we have to take. Now, with the first model, when I took the derivatives, when I got the first order conditions, remember I did 1 over the entire constraint written out. But if that entire constraint written out is just equal to CT, then it's just 1 over CT, right? So what I'm going to do is, if you remember, everything that's purple here is equal to CT, then the derivative of the natural log of everything in here is 1 over all the purple stuff, which is equal to CT. Right, so what I'm going to do is I'm just going to write out CT equals AT times KT to the alpha plus MT minus 1 plus pi t, MT plus 1 plus BT minus 1 plus RT inverse, or 1 over 1 plus the real interest rate, times future bonds, minus future capital plus current capital, plus tau t. Right, so CT is equal to all that. So I want you to keep that in mind as I take these first order conditions, because if I were to take the first order conditions and write this thing out for every single one of them, one, I would run out of board space. I don't really have a very big board, much to the chagrin of General, what's his name? Is it Turgidson, I think? General Buck Turgidson from Dr. Strangelove. You can't let that risky in here. He'll see the big board. If you haven't seen the movie, it's absolutely phenomenal. Such a great movie. Anyways, first order conditions. Oh, I guess I didn't really get to finish my thought. Not only did I not have the board space to write this out every single time, it takes a very long time to write that stuff out. And I would much rather take that valuable time and do, I don't know, other stuff with it. So what I get is well, there's three derivatives, sound it out, Jeremy, that I have to take. Capital, money, and bonds. How do I know that? Because the arguments inside this value function are capital, money, and bonds. So you can take them really in any order you want. I'm doing it with capital first. Right? So it's the same idea as what I did before. I got this derivative of the value function with respect to KT plus 1. Right? Because capital is a state variable. I can't choose capital, like today's capital, I can't choose today's capital stock. I can only choose tomorrow's capital stock. Therefore, derivative of the value function with respect to future capital, KT plus 1. And that is going to be equal to, well, 1 over CT. Derivative of the natural log of this shit is just 1 over this stuff, but this stuff, remember, is equal to CT. But then I have to do the chain rule, right? So I got to take the derivative of the inside of this thing, which is the derivative of consumption with respect to capital, which is just negative 1. So I'm going to have negative 1 over CT plus, all right, well, let's see what's going on here. All right. Theta natural log of MT, well, that's, I haven't substituted anything in for MT, it's just real money balances. So that just goes away, right? That differentiates to 0, which means I just have this thing. I get negative 1 over CT plus beta times the partial of this value function with respect to KT plus 1, and set that equal to 0. Okay, so far so good? Let's do the next one. Let's take the partial with respect to money. Now, just like with capital, today's money balances were determined yesterday. So money is also a state variable. Today's money balances were determined yesterday, so tomorrow's money balances are determined today. Therefore, I take the derivative of this value function with respect to future money balances, MT plus 1. Well, what do I get here? Well, I'm going to have 1 over ct, right? Derivative of the outside, natural log of this stuff is just 1 over that stuff, 1 over ct. But now I have to take the derivative of what's inside and multiply that by 1 over ct. So let's look at ct. Where do we see an mt plus 1? Oh, boom, here's an mt plus 1. Right? Okay, mt plus 1. What's the derivative of that? Well, it's negative 1 plus the inflation rate. I'm going to bring this negative out here. Actually, just for the sake of consistency, I'm going to keep the negative there too. So I get negative 1 over ct times the derivative of the inside, which is 1 plus the inflation rate. Like that. All right, now I go through the rest of this thing. I've got the derivative of everything in purple. Is there an mt plus 1 there? Goes to 0. So now I add beta times dv of kt plus 1, mt plus 1, and bt plus 1 with respect to mt plus 1. And let that equal 0. Okay, so that's the first order condition for money. So we've got capital and money. Now we need the first order condition for bonds. Okay, well again, 1 over ct. But now I've done the derivative of the outside, chain rule, got to do the inside now. So what's going on the inside? Well, let's see, where do I have a bt plus 1? Is it, oh, shit, it's right there. Negative 1 plus rt to the negative 1. So again, I multiply this 1 over ct by negative 1. And I also multiply it by 1 plus the real rate of interest rate to the power of negative 1. Okay. Now I keep going through, I keep scouring this thing. There's no more bt plus 1s here because that's the only one that we see. There's no bt plus 1 here, so that goes away. Good. There is bt plus 1 here. So what do? Well, I add beta times the partial with respect to bt plus 1. So these are the 3 first order conditions I get. But remember, we don't know what either this, or this are. We have no clue what they are. So what do? Well, same thing we did before. We just take 3 more derivatives, we update in 1 period, plug them in. So let's start with capital. All right, what do I get with this? Well, I get 1 over consumption times, well, what is the derivative, the inside, all right, ct is a function of this stuff, what's the derivative of that with respect to kt? Well, how many kts do I have? I've got this in production, and then I've got the existing capital stock. So, the derivative of this guy is just like what we saw with the first model of this particular variety. Alpha times at times kt to the alpha minus 1. All right, where's the next kt? Well, there's this 1 plus delta kt. Cool. Or sorry, 1 minus delta kt. Like that. Right, so it's 1 over ct times the marginal product of capital less depreciation. Okay. I'm going to do this little implies sign here to update it one period, where all I do is just add 1 to all of these subscripts. And I get that. So actually this is exactly the same as what we saw with the first model. Not too bad, is it? I need to be more conscious of when I'm actually in view of the camera. Although it's nice now because I actually have a screen behind me that shows me where I am and where I'm not. But anyways, enough about that. Let's do the derivative with respect to money. Now this one's going to get a little wonky. It's going to be a little different. Because, well, I got to first go through, I do my 1 over CT. You're probably noticing a trend here with this 1 over CT. It kind of shows up a lot. All right, so I got my 1 over CT. But instead of doing it with respect to mt plus 1, now it's just with respect to mt. All right, well, where do I see an mt? Well, there's this here. All right, so what's that? The derivative of mt with respect to mt, well, it's just 1. So I get 1 over ct. Okay, that's nice. That makes me really happy, actually. All right, but let's see, what else do I have? Well, I've got plus theta times the natural log of mt. So I'm going to get theta times 1 over mt. Now if I want to update this one period, well, I get 1 over ct plus 1 plus theta times 1 over mt plus 1. Finally, bonds. Okay, so what do I do here? Well, again, I do 1 over CT. Okay, now I look through CT and look for everywhere that I see a BT. Well, again, the only place I see it is right here, BT. The derivative, positive BT, is just 1. So this is actually just equal to 1 over CT. That implies right. Okay, well that looks like a lot. That's because it is a lot. So here's what I am going to do. I'm going to erase everything from here down and rewrite it in terms of the updated derivatives. So for this half of the board, it's the 3 first order conditions that we needed and then the 3 other derivatives we needed that are updated one period in order to be able to figure out what this, and this are. So give me just a moment to erase that. Actually, I'll do it in purple. So you can see that what's in black are the first order conditions. What's in purple is what we need to substitute back in for this, this, and this. You know what? Now that I think of it, I need to color code this as well. So that one's in purple, but I'm not so much a cheapskate. I can use other colors too. Let's use light blue. Who doesn't like light blue? I love light blue. I guess for money I should have just used green, but whatever. Alright. And then finally, we will have, let's see how orange looks. Big color of my alma mater. You can't tell by my hat. Let's see, how does that look? Yeah, looks good to me. Which means now I just need to write this sucker in orange as well. So we can see exactly where these things are supposed to go. Like that. So now that we see where they're supposed to go, it makes this a little bit easier. All right, now all I have to do is just what's purple, plug it in. What's blue, plug it in. What's orange, plug it in. That implies what I'm going to get is, I'll rewrite this entire thing only with the purple plugged in. almost done. Okay, so finally, what we got? Euler equation for capital. Looks just like the Euler equation we saw in the other model. There's actually a reason for that. 1, utility is additively separable. 2, constraint's linear. There are no nonlinearities in the constraint, and the constraint is additive. So we can add as much shit as we want into that constraint and take a derivative of that thing with respect to, say, capital, and everything that's not capital, well, differentiates to 0 because it's being added in. There's no no multiplicative behavior, no multiplicative relationships between these guys. Well, doesn't matter. So the Euler equation, capital, will be exactly the same in this case. All right, let's look at money. This is the Euler equation for money. Well, it's negative 1 over CT times 1 plus the inflation rate, plus beta times 1 over CT plus 1, plus theta times 1 over MT plus 1. Make sure when you do this, beta is being multiplied, the sum of these things. Both of these guys are multiplied by beta, right? And that's, again, equal to 0. Finally, negative 1 over CT times 1 plus R to the inverse, or 1 over 1 plus R, plus beta times 1 over CT plus 1 is equal to 0. So with all that, right, let's solve these things, right? Let's just move this negative 1 over CT in each of these equations over to the other side. So I'm going to clear up some space, clear some space, clear some space. So much space to clear. Oh, so much space is now cleared. In case you ever wondered if the COVID lockdowns make people start going crazy, it's made me start singing to myself when I teach. Actually, shit, I don't even need that part anymore. All I need is 1 over CT equals beta times 1 over CT plus 1 times the marginal product of capital less depreciation. Like that. That's the Euler equation for capital. Let's do the Euler equation for money. Well, again, 1 over CT. Not exactly how I want to write this one out. So here what I'm doing is I am subtracting this from both sides and then dividing by 1 plus the inflation rate. So I got 1 over CT equals beta times here. We get that, and now finally, Euler equation for bonds. Now again, I'm adding 1 over CT times 1 plus RT to the negative 1, both sides, and then multiplying that 1 plus RT both sides, giving me beta times 1 plus the interest rate times 1 over CT plus 1. So now, after all that math, I love math. Oh my math, so much math. This is what we get. These nice 3 simple equations. The first one is the Euler equation for capital, for investment, right? It's going to explain the flow of consumption over time with respect to investment, right? So it's going to explain how consumption is flowing over time, right, evolving over time, so to speak, along the dimension of capital accumulation, right? Because we can spend our stuff, right? We can spend our resources in a number of ways now. We can consume, get real money balances, get capital, get bonds. So we're looking at how consumption can change relative to how capital changes, right? Thus investment. We can look at how consumption will change relative to how real money balances will change, which is that second equation. And finally, we look at how consumption changes when it comes to bonds, which is that third equation. Now that third equation should look pretty familiar because the first thing we did with dynamic optimization was, well, something that yielded that third equation. All right, 1 over CT equals beta times 1 plus R times 1 over CT plus 1. Now from these 3 equations, we can get our steady states. And these steady states will have some rather interesting properties to them. And there's one property in particular that is going to be very, very, very interesting for us. Now, which one do I want to do first? Well, I don't know about you, but personally, I'm kind of feeling like doing that first one first. Because we already know what it is. Right? If you were to look through your notes for the previous dynamic general equilibrium model we did, right, steady state capital is going to be the same. Exact effing same. So let's find the steady state for capital first. Now remember, in the steady state, right, we want this fixed point for capital. Anything with a t subscript or t plus 1 subscript just gets an ss subscript. So 1 over CSS equals beta times 1 over CSS times alpha times my wordy dird times KSS to the alpha minus 1 plus 1 minus delta. Right, multiply CSS by both sides. 1 equals beta times alpha times my wordy dird times KSS, alpha minus 1 plus 1 minus delta. Right? Okay, well I want KSS, remember, right? So I want KSS isolated. So I'm going to do, let's see, divide both sides by beta. One over beta equals this, marginal product of capital less depreciation, like that. Well, now I can subtract this from both sides. Right? Actually, let's figure out what this 1 over beta is. Remember, beta, 1 over 1 plus rho, right? That hasn't changed for this model, just like it didn't change for the last model. So beta to the negative 1 is just 1 plus rho. So 1 over beta is beta to the negative 1. It's just 1 plus rho. Right, minus 1 minus delta equals this. Well, let's see, go through. 1 minus 1 is 0, rho plus delta. So that gives me this. Rho plus delta equals my just straight marginal product of capital. Divide both sides by alpha times A. Right, which then just gives me steady state capital being equal to rho plus delta take that back. So remember, alpha minus 1 is a negative exponent, so if you just multiply the exponents by negative 1, right, so if I raise this to negative 1, the alpha times my bad word over rho plus delta to the power of 1 over 1 minus alpha. Right, and if you don't remember exactly what I did there, you can go back to the video that lectures on the dynamic general equilibrium, steady state stuff, and you should be able to find it rather easily there. But that's our steady state capital. Okay, so now that we have found steady state capital, it's now on us to find steady state output. We could try to find some other steady states first. Steady state output seems to be the best one to go with. So steady state output it is. Okay, what is steady state output? Well, if you remember output, output, when it's not in the steady state, is equal, well, it's like not in the steady state, and I put it in steady state. Good one, Jeremy. Good job. Output, when it's not in the steady state, is equal to that. Yt equals At times Kt to the alpha. Well, in the steady state, it's just Yss equals a wordy dird times KSS to the alpha. Well, if we know what steady state capital is, all we have to do is plug it in. just like we saw in that first dynamic general equilibrium model that we went over, right? The one with the infinite horizon, not the one with exogenous output, but the one with output that had been endogenized. Well, that's exactly the same. Now, some of you may see where this is going. Some of you may not. And if you don't feel bad, because I didn't either. So, let's think about the steady state values for inflation. In case you're wondering where this jump was, it totally had nothing to do with the fact that I made a giant screw up or anything like that, because obviously I'm, above such things. Right? But in the steady state, real money balances will be constant. It implies prices will be growing at the same rate as the nominal stock of money. And because changes in the nominal quantity of money will be done by lump sum transfers to the public, right, the real value of these transfers in terms of money must be equal to this. Now, after a little bit of algebra, I'm not going to go through too much here because, well, I've already kind of hammered you guys with a lot of algebra. I don't need to do any more. I'm going to say this implies that if we're looking at the transfers, net of taxes, we would get this. Right, so if we want steady state inflation, how are we going to do that? Well, let's see. 1 plus pi SS times tau SS equals pi SS times MSS. Well, we divide both sides by tau and both sides by pi. Evaluate this stuff here. Gives me that right there. Cool. So what does all that mean? Right? What is that telling me? Well, what this says is that steady state inflation is determined by the change in steady state real money over, not the change, geez. The steady state of real money divided by the steady state for transfers net of taxes, minus 1, to the negative 1. So it's 1 over all that stuff. Well, what does that mean? Well, what this tells me is that inflation is determined by money balances and by transfers. Okay. That's kind of cool. In fact, That's like extremely interesting. Why? Well, one second here. Okay, anyways, yeah, so this stuff's pretty interesting. This is getting more and more interesting as we look further and further into it. Now, in the notes, it says that using, let's see, what is it? This identity right here. We use this identity, it actually reduces the constraint. So the steady state for transfers net of taxes. And if I'm not doing the algebra on this, you are definitely not doing the algebra, unless you want to. You can, but you don't have to. But it reduces this constraint, right, that really long constraint that we had earlier, down to something really simple. And what is that? Well, steady state consumption equals steady state output minus delta times steady state output. Okay, what does that mean? Well, it actually means some pretty cool stuff. And this is where the really neat stuff comes in. So, let's break this down into a slightly different way. Okay? So we know what these steady states are. Well, we don't know what all the steady states are, but we know what some of them are. And the interesting thing about all of these steady states, let's look at the steady state for capital. Right? Capital is a real variable, right? It's tangible. You can touch it, you can hold it, you can use it. Maybe you can't hold it, it might be kind of heavy. But it's you can touch it, you can use it. It's a thing, it is a real thing, right? It's a real variable. Output is a real variable, right? It's a thing that you can use. Because you can split output up. Like output is what you earn, output is your income, right? So capital and output are real variables. But money is a nominal variable. Now we can put money into real terms, like real money balances, right? That's just money that's been adjusted for inflation. But at the end of the day, money is a nominal variable. So money's nominal. Bonds are nominal. Well, inflation, yeah, definitely nominal. Right? Do you notice anything here? Look at the steady states for output and capital. Do you see anything for inflation or money in there? By that same token, do you see anything for bonds in there, right? The government wants to borrow money, right? When we talk about recording equivalence and the timing of government expenditures, right? Well, we're actually kind of seeing it in action here because bonds aren't in that steady state either. So monetary policy in this particular model doesn't have any impact on real variables in the steady state. In addition, fiscal policy measures have no impact on these steady state variables. They're the real variables that are in the steady state. In fact, you really can't tell a difference at all between the steady state output in this model, and steady state capital as well, and steady state output and capital in that first one, the neoclassical growth or neoclassical business cycle model. Can't tell a difference. Why? Because, well, there isn't one. And this isn't to be like, oh, look at all this work that we did, haha, it's not real, none of this matters. No, it's not like Ad Astra, right? I don't know if you've seen that movie. I have. I enjoyed it, don't get me wrong. I enjoyed the nihilism in the movie, but it was kind of like Brad Pitt does that entire trip ultimately for nothing. It's just the whole thing is for naught at the end. Why did he do any of that? Well, no one really knows, right? He thought he was doing something, but then he got there and realized that there was absolutely no importance in really any of the movie whatsoever. It just didn't matter. I don't want to give you that impression here, because in that movie, the fact that nothing really happened at the end was cool in like a neat little artistic way, but this has some rather interesting implications. And the implications are the following. Well, first, let's look at this constraint in the steady state. There's no money, there's no bonds, there's no transfers net of taxes. This is the really cool thing about this. I don't know if I want to keep these first order. Yeah, I'll keep the first order conditions up. What the hell? So, steady state capital and output, right, are real variables, are not in any way a function of money growth, inflation, or transfers net of taxes. Well, that implies something really interesting here. This is where we get to the steady state properties of this particular model. And actually, you know what? I'm going to rewrite now you'll see something that looks a little different in the text for steady state capital, steady state output. I assure you, algebraically, they are the exact same thing. Steady state output is equal to A times that stuff. So steady state consumption is just the difference between steady state output and steady state investment, just like before. All right, this is what we get. So capital, output, consumption, and thus investment as well, are in no way, shape, or form functions of money or inflation or bonds or transfers net of taxes. This is where the steady state properties of the model come into play. Definition time with Jeremy. Well, a model is said to exhibit monetary neutrality if the steady state values for the real variables are unaffected by changes in the nominal stock of money. Right? If you were to change the nominal stock of money, is that going to affect steady state capital? The answer is no. It's not in steady state capital. Right? If steady state capital is not a function of it, well, who cares? It's not going to do anything to real variables. Steady state output's the same way. It's not going to do anything. All right? Steady state consumption, again, is not affected. So in the steady state, capital, output, consumption, investment, right? All the variables that we looked at in the neoclassical growth or neoclassical business cycle model are totally unaffected by inflation or changes in real money balances. So in this case, there is no trade-off between inflation and unemployment like we talked about at the beginning of the course with the Federal Reserve being tasked with managing inflation and unemployment, right? That dual mandate. So according to this model, the dual mandate is garbage. Right, so according to this model, this dual mandate isn't going to do a damn thing. Okay. Well, this is just like a one-time change in the nominal stock of money. What about a change in the growth rate of money? Well, the model exhibits monetary superneutrality if real variables in the steady state are not affected by a change in the growth rate in the nominal stock of money. So monetary neutrality says if we change the level of nominal money balances in the economy, we will see absolutely no change in real variables in the steady state. Monetary superneutrality says that if we were to change the growth rate in the nominal stock of money, again, there would be no change in any of the real variables in their steady states. Well, that's pretty interesting to me. Because, I was led to believe, I always thought that monetary policy had real impacts on the economy. Right? What about all that research that's out there that says monetary policy has real impact on the economy? Right? What about even my own research? My dissertation research. If any of you actually want to read it, I'd be more than happy to send it to you, although we will be talking about pretty much all of it at some point or another in this course. Even with that, right? If I were to look at that research that I did personally, right, that I spent 4 years of my life working on, actually close to 5, almost 5 years of my life working on, that says monetary policy has real impacts on the economy, what the hell? This model says otherwise. So who's wrong, me or the model? Well, turns out neither. I'm right, and the model's also right. Because, well, there's a couple of places where the model falls apart. We'll be discussing that relatively shortly. I believe the next lecture, actually, we'll be discussing that, where the model kind of starts to fall apart a bit. But, in addition to that, this is in the steady state, sort of assuming like a long-run trend, a long-run pattern. Right? Well, in the long run, if you remember anything about what Keynes said, like an intermediate macro, right? Keynes said in the long run, we're all dead. Well, here in the long run, we're looking at changes to this stuff in the long run, basically, and, well, there's nothing really happening in the long run when it comes to how nominal and real variables interact. Nominal and real variables will definitely interact in the short run, but they don't do so in the long run. So this isn't a bad model. This is not at all in any way, shape, or form a bad model. It's actually a very good model. It's just very good for the predictions of medium to long run behavior. It's not very good for predictions for short run behavior. But again, we'll be getting to that a little bit later. So if real variables aren't affected by inflation, what will be? What is affected by inflation? Well, nominal variables will definitely be affected by inflation. Right? Because under monetary neutrality, what we can sort of think of here is that when we have inflation, right, the nominal variables are picking up all the slack. Right? The nominal variables are doing all the work, so the real variables don't really have to, right? It's kind of like if you've ever had like a group project, right, and there was that one guy that was like a total screw off, didn't do anything, pissed everybody else off. Well, everybody did all the work, right, because, well, they had to. The work had to get done. Now, inflation will change variables. It will just, in the long run, in this model, all it's going to change will be nominal variables. It won't change any real variables. So, okay, let's think of it this way. The interest rate on any asset that pays off in units of money at some future point will be affected. The real value of those future units of money will be affected by inflation, be reflected in the interest rate required to induce individuals to hold the asset. Okay, consider the nominal rate an asset must yield if it is to give a real return of lowercase rt in terms of consumer goods. That is, an asset that costs 1 unit of consumption in period t and yields 1 plus r units of consumption at period t plus 1. Well, in units of money, this costs piece of t units of money at time t. Since the cost of each unit of consumption at t plus 1 is pt plus 1, in terms of money, the asset must pay an amount equal to this. Let me write all of that down instead of just flat out reading it to you. So, consider an asset pays off in units of money at a future point, right? The real value of future units of money will be affected by inflation. So this gets reflected in the interest rate that induces the agent to hold the asset in the first place. So we've got the nominal interest rate. Let's see. Capital RT. Must return a real yield of lowercase rt in terms of consumer goods. So if it costs 1 unit of consumption today, so it costs 1 unit of, we'll say, CT, in yields one plus RT units of CT plus 1. In terms of money, it costs piece of T guarantee. The cost of a unit of consumption, cost of each unit of consumption, tomorrow, Ct plus 1 is P sub t plus 1 then in order to induce this agent to hold the asset, right, the bond, then the asset must pay an amount that is equal to 1 plus r times pt plus 1. So the nominal return on that asset is 1 plus r, pt plus 1 minus pt divided by pt. All right, so it's really 1 plus the real rate of interest times tomorrow's price level minus the current price level over the current price level. This comes out to this. 1 plus r times 1 plus pi minus 1 is equal to the nominal interest rate. So this is the nominal rate determined by this right here that will induce an agent to hold a bond. Now, obviously that's a function of inflation. And if I were to put this in the steady state, again, we would see it is a function of inflation. So if I want to hold a bond, well, I'm going to have to get some interest rate, some nominal interest rate being quoted, but it also must yield a real interest rate, lowercase r, in order for me to in order to induce me to purchase that bond. Now, let's think about the Euler equation for bonds. Well, it was this. In the steady state, I get this right here. And if I were to try to find what the steady state is, well, 1 over CSS, 1 over CSS, multiply both sides by CSS. So I get CSS over CSS, which is just equal to 1, right? Equals beta times 1 plus the real interest rate. Well, beta is equal to 1 over 1 plus rho. So really, if that's the case, this thing is really equal to 1 plus r over 1 plus rho, which is equal to 1. Which means 1 plus rho equals 1 plus r, rho equals r. Right? So my patience also matters here, right? How patient I am. Do I want to consume more today? Do I want to invest? Well, if I want to invest, right, if I want to buy capital, okay, the rate of return on that is going to have to be the marginal product of capital. If I want to buy a bond, right? Well, the interest rate on that bond is going to have to yield a real interest rate that is equal to exactly how impatient I am, which will determine whether or not I buy it, right? Because we got the interest rate, the real rate here. Therefore, the inflation rate has to be one such that the nominal interest rate that I see that induces me to buy the bond, well, is one that induces me to buy the bond. Because I have to give up units of consumption in order to get that bond. And to give up units of consumption today, right, I have to be given some promise, some reward to be able to consume more tomorrow. Because otherwise I have no incentive to do so. And if I've got no incentive to do so, why in the hell am I going to do it? Right, so the interest rate has to be equal to, the real rate has to be equal to how impatient I am. Right, and the real rate is just really the nominal rate that's adjusted for inflation. Okay, so where is that going? Well, it's going somewhere pretty interesting. Well, for one, we can rewrite some of this stuff. Let me show you another way to write the nominal interest rate in the steady state. Well, because of that relationship that we had between how the real interest rate depended on how patient or impatient I was, you can do a little bit of algebra. Don't worry about the algebra. I would just remember this guy right here. Because there's something kind of cool with this. Right, so this is the nominal interest rate in the steady state, and it's equal to 1 plus steady state inflation over beta minus 1. This means that the nominal interest rate in the steady state varies 1 for 1 with inflation. So, if we were to change inflation, we will change the nominal interest rate. So it seems like we still have a lot of moving parts. Even in the steady state, we've got a lot of these moving parts. And kind of makes you wonder, like, is there a unique steady state for all these things where everything is nice and like at rest and nice and even? And the answer would be yes, there is. But it really kind of depends on certain like initial values that we put in, how we calibrate the model, etc. But yes, there is in fact a set of steady state values for all of these variables that matter. That not just matter, but are unique. Right? We can uniquely solve this model. But, well, I'll tell you what. Give me one moment. I shall return, said once the great Julius Caesar. It didn't work out well for him. Let's hope it works out better for me. And I have returned. Okay, so where is this going now? Well, this is going down a path where we're going to be concerned because really, okay, we can uniquely solve for a steady state in all these. But at the same time, I was like, well, it all depends on what some of these initial values were. true. Right? This steady state that we're currently in, right, if we have different initial values, we'll have different steady states. Now, analytically, the steady states will be solved out the exact same way. Just if we put different values in for, capital R, lowercase r, pi, output, capital, etc., right, we'll get different sets of steady state values returned. So one of the things that's so nice about this model is that it's so malleable. We can do a lot with it. And so when we're looking at this, well, we get kind of an interesting question. This is a question that's been posed by a lot of people over the years. The most famous one to pose this question is a guy by the name of Milton Friedman. Now, if you have not heard of Milton Friedman, I highly suggest you go read about Milton Friedman. He is, in my opinion, one of the greatest, if not the greatest, macroeconomists to have ever lived. The man was an absolute genius. Now, he's not super famous with everybody. Quick little history lesson. It's not entirely complete or exhaustive. But Milton Friedman was a professor of economics at the University of Chicago. He was an economist who sort of helped push or help get started the monetarist school of economics, right? The school of thought in economics. Now, there's a lot the monetarists got right, there's a lot the monetarists got wrong. Excuse me, just like there's a lot the Keynesians got right, a lot the Keynesians got wrong. Right? No school of thought is 100% right or 100% wrong. Now, some are more wrong than others. For example, like the Austrian business cycle theory is generally wrong, and laughably wrong at that. The Marxist school of thought is, again, laughably wrong, but they still get like one or two things right here and there. I mean, it's probably more, they get less right than you would just by doing a coin flip. That tells you anything. So they're not even right by chance, technically. Just sad. But enough shitting on the Austrians and the Marxists. And I shit on them equally, by the way. I'm sure a lot of you know about Marxist economics. Maybe some of you know about Austrian economics. It's a very far-right, hardcore libertarian school of thought that basically says everything needs to be totally left up to the free market, and with the exception of very extreme circumstances. This goes so far as to say that even the central bank should not exist. Or if it does, it should exist to maintain a gold standard, and that's it. Therefore, we should have a private currency. Not a very good idea. Take my word for that. It's not a good idea. Now, enough about that. More about Milton Friedman. Why wasn't he that popular? Well, I mean, he was incredibly popular. He got a Nobel Prize in economics. My dissertation advisor, Jerry Dwyer, was actually Milton Friedman's last student when he was at Chicago. And this was in, I believe, 1981. And that is my dissertation chair. So I am the academic grandson of Milton Friedman. Therefore, I'm probably going to have a lot of nice things to say about Milton Friedman. He was a brilliant monetary economist, and he and another economist, Anna Schwartz, in the 1960s, I believe it was 1968, wrote A Monetary History of the United States. And it was phenomenal. And a lot of his work gained a ton of attention in the academic community, as well it should have. And a lot of it was in monetary, but a lot of it was also in other macro theory stuff, right? Like the consumption function, which we'll talk about a little bit later. He did a lot of seminal work on that, and the permanent income hypothesis, something that we'll also be talking about. That's thanks to Milton Friedman. The guy was a genius. But one of the things that he asked was really, what is the optimal quantity of money. Right? Because we can have multiple quantities of money in this model, right? As I said, depending on what our starting values are, we'll get different actual, like, hard values for the steady states, depending on where we start. Right? Where you start determines where you go, where you end up, and how you get there. But big question was, what is the optimal quantity of money? Milton Friedman asked this question. He asks this question fairly frequently. Fortunately, for him and us, not only did he ask this question, because asking the question is pointless if you don't eventually get an answer to it, right? I can ask, what is the meaning of life for the rest of my days, right? I can ask anybody I want, what is the meaning of life? I can ask my cat. I can ask Isis what the meaning of life is. You know what she'll probably tell me? Meow. I don't know how to translate that, do you? Exactly. Questions without answers are bullshit questions. This is not a bullshit question, because according to Milton Friedman, under certain situations, namely the circumstances, the situation that is described by the money in the utility function model, by the economy that the MIU model encapsulates and explains, right, under the conditions listed in that model, well, it really comes down to finding a better way to ask it. Right, what does the Federal Reserve do? What does the monetary authority do? Right, do they actually control the money supply? Well, the answer to that technically is no, they don't. What do they control? Well, they control the money base, which may or may not become the money supply. Sometimes it can, sometimes it can't, right? Depends on other factors. So why are they controlling the money base? Well, they're controlling the money base to try to achieve a target interest rate on money. This iced tea is phenomenal, by the way. You can't drink too much of it. It's very strong flavor. It's a very strong kick to it. You gotta enjoy it in sips. But my God, is that iced tea delicious. Wow, it's good. And the name of the iced tea is... Oh, what do you know? It's not iced tea. It's Maker's Mark. Oops. These hilarious ramblings brought to you by Maker's Mark. Thanks, Maker's Mark. I'm so getting fired. So a better way to ask this question is, right, if they control the money base in order to try to achieve a target interest rate that determines a target rate of inflation, maybe a better way to ask this then what is the marginal cost of printing one more unit of money? Right? What's the marginal cost the central bank faces by printing an additional unit of money? Well, let's think of it this way. The interest rate on money, the interest rate on holding money for some period of time, let's say overnight, right? The federal funds rate, right? That's an interest rate on money, isn't it? It's an interest rate on holding cold cash. It's the opportunity cost of holding idle cash, to be honest with you. Well, that's the marginal cost of holding 1 unit of cash overnight. But what about the marginal cost of printing a unit of money? What about that? What is that? Well, in this case, Milton Friedman argued that it's the nominal interest rate. Capital RT. So the nominal rate of interest is the marginal cost of printing one more unit of money. Now let's think about this, right? In the Federal Reserve, you indirectly control the money supply. You want to introduce one more dollar ultimately into the money base, which will eventually find its way to the money supply, possibly. And I say possibly because of some of the unconventional monetary policy stuff that's been going on, which is where really the last portion of this course will be focused, is purely on unconventional monetary policy. But the marginal cost of adding one more dollar into the money base will be the nominal interest rate, RT. All right, and by the Fisher equation, now, I initially had, in this model, what I initially had in this model was something akin to the following. I'll make sure I get it just right, because it would be disastrous if I did not. This right here. So 1 plus the nominal rate divided by 1 plus the rate of inflation is equal to 1 plus the real rate. Now, probably like, okay, what the hell? Thought the Fisher equation was something a little different. Well, it's kind of where we go from like a continuous time to like a real time, back to continuous time to, not real time, geez. Discrete time, continuous time, discrete, continuous, etc., kind of so on and so forth. Well, this sort of implies that the real rate, and this is the real Fisher equation I'm going to want you to actually consider. Right, this is the one everybody knows. The real rate of interest equals the nominal interest rate minus the rate of inflation. Right? Why am I subtracting inflation rather than dividing by inflation here? Well, it comes to like linear approximations, log linear approximation stuff. It fairly loosely, not very loosely, kind of loosely, implies that the real interest rate is just simply equal to the nominal interest rate minus the rate of inflation. Now, this right here is where the interesting thing comes in. Milton Friedman asked, what's the optimal quantity of money? Like I said, the better way of asking it is, what's the marginal cost of printing one more unit of money? Well, if that marginal cost of printing one more unit of money is the nominal interest rate, the question then comes down to, what is the nominal interest rate supposed to be equal to, right? On the margin, what is it going to cost the central bank to essentially print one more unit of money? Well, they're printing millions and millions and millions of dollars, or millions of units of money on a pretty regular basis. On the margin, if we did one more unit, what would that really be equal to? right? Think about just printing cash, right? You go to one of those like presses, like the mint, where they're printing all that money, right? And we're assuming that they're only printing, let's say, dollar bills for a moment, because I know there are bills in different denominations, but let's just assume it's all in one denomination, one unit of money. So $1 bills. They're printing out these massive sheets of $1 bills, right? What is the marginal cost of one additional dollar bill? Not the sheet, just the dollar bill. What's the marginal cost of that? Well, I don't know about you, but I'd venture a guess that it's probably 0. And Milton Friedman did the exact same thing. He also ventured to guess that it was 0. Now, when I said I'd venture to guess that it was 0, it was because, well, I kind of already knew what the answer was, and it's 0. Right? The marginal cost of printing another unit of money, one more dollar, is equal to 0. Now, Friedman argues, and I agree with Friedman on this, that in this case, this particular case, the optimal quantity of money is achieved when the price is equal to the marginal cost. Right? The optimal quantity of money is achieved when the price of printing money is equal to the the price of money is equal to the marginal cost of printing money. So this actually goes back to microtheory, doesn't it? But what is there in the case where price equals marginal cost? What happens when price equals marginal cost, right? What causes this condition to hold? Well, you have perfect competition. No firm has any market power over any other firm, right? Price is simply equal to the marginal cost of producing that unit, one unit of whatever good that is. We have perfect and complete information. No signal extraction problems. Right? We have none of that shit that we have to worry about. We have no informational asymmetries. There's no monopsony power. Factor markets are perfectly competitive, meaning capital and labor markets are perfectly competitive. So capital markets, in capital markets, the marginal product of capital is equal to the real interest rate. The marginal product of labor in labor markets is equal to the wage rate. Right? So we have all these assumptions here, which aren't necessarily met in the real world, but in this particular model, in this particular sort of like this like heaven view of the way the economy should work, this paradigm, right, of the way the economy should work, under that set of assumptions, right, and all of these assumptions, by the way, line up with the money and the utility function model. With these set of assumptions being satisfied, where price is equal to marginal cost, if the marginal cost printing another unit of money is 0, then if price equals marginal cost, the marginal cost of printing money is 0, that implies that the nominal rate of interest should be equal to 0. So if the nominal interest rate is equal to 0, and we look at the Fisher equation, I take that Fisher equation and plug RT equals 0 in, well, it says that the real rate, if the real rate is equal to the nominal rate minus the rate of inflation, the nominal rate is equal to 0, that reduces down to the real rate equals the rate of deflation in the economy. That, everyone, will achieve the optimal quantity of money. Because if the price is equal to the marginal cost, we will get the optimal quantity of any good. Money is a good. So if the price of money equals the marginal cost of printing money, the price is equal to 0, then plugging this into the Fisher equation, right, which the Fisher equation is used quite regularly in the money and utility function model, which is really an extension of a class of business cycle models known as the real business cycle model, which we'll talk about in the next lecture. Basically, under the real business cycle model, we're assuming that the majority of shocks that affect the economy come from real factors, namely like supply-side shocks. Right? It's not to say supply-side economics, like in the way that I'm sure you're probably used to hearing it, like quote-unquote trickle-down economics, which is it's an infuriatingly bullshit thing to compare that to supply-side economics, because those two are not the same. Trickle-down's like, give the rich money and it trickles down to the poor. Supply-side economics says majority of economic shocks are explained by, well, supply-side factors. Can't really compare those two. But anyways, getting off on a tangent again. By the Fisher equation, the real rate of interest equals the negative of the inflation rate. So we would actually see a rate of deflation, but that rate of deflation would be equal to the real rate of interest. So if the real interest rate was 2%, right, if you're earning 2% on any particular asset, right, that goes through that process I was explaining earlier, right, if you're getting 2% on that asset, well, then the rate of inflation would actually be negative 2%. Now, that will wrap up this lecture on the money and the utility function model. We will next be going into, I believe, empirical tests of this model, or maybe we'll go into the real business cycle model. I don't remember exactly what the next chapter is. But whatever comes next is, well, whatever comes next. Maybe we'll look at some stuff with a government budget constraint. Maybe we won't. Actually, you know what? Yeah. Whatever comes next is whatever comes next. If something comes that's not in the book, trust me, you will get lectures. Like, you will get a written treatment of all of this stuff before I even record a lecture. Now, what I would be on the lookout for in the meantime is the following. 1, a problem set. Now, I understand that my cat Isis got really sick, and that kind of ate up a lot of my time for a while trying to deal with it, because it was an incredibly costly venture, we'll say. It's going to cost quite a bit to make sure that she is on this nice road to recovery that she's currently on. I had to set up a GoFundMe. It was actually surprisingly easier than I thought it would be, but it was still pretty rough. And, you know, I still got to make pretty regular trips to get these special vials of this drug that is ultimately remdesivir. So for anybody who's been keeping up with current events with coronavirus, remdesivir is used to treat coronavirus. Well, FIP is actually a mutation of the feline coronavirus. So if remdesivir works on coronaviruses, then remdesivir is going to work for FIP in cats. So yeah, it's been a lot of work. And that's no excuse for the fact that I kind of slacked off for the last like 2 weeks on this. I haven't really given you any real like homework assignments. I haven't given you anything to do. So the next homework assignment I would be on the lookout for will first just have you solve a basic dynamic general equilibrium problem. I'm going to give you a hint. It's probably like really, really, really close to what you saw earlier. Probably extremely close. Perhaps identical. I don't know. Maybe I might change one or two things. But whatever I change, I promise it won't be a big deal. Now, in addition to that, I'm also going to have some stuff on money and the utility function. If it's anything that went on the board, for the most part, consider it to be fair game. That doesn't mean you have to derive the constraint yourself. It does mean you'll probably have to convert the constraint from nominal to real. But if you understand, like the Fisher equation, and you understand, okay, well, if I got to multiply stuff basically by 1 in some cases, in order to get these time subscripts to line up, then you should be fine, right? Honestly, if you just follow what I did in the lecture, then I promise you will be in extremely excellent shape on this homework. And then I'll have a couple of more intuitive questions, stuff to try to think about. Now, the next lectures that follow, again, I'm not entirely certain what's going to happen, whether it's going to be empirical tests of this model, whether it's going to be a way to look at this in like a static form so we can actually sort of get pictures out of what's going on here. I haven't entirely decided on that yet. Maybe it's going to be pictures. I think pictures sound like a good idea. Pictures sound like a really good idea. Because pictures help everybody. And we're economists. We love to draw pictures, right? Who doesn't like to draw pictures? So I'm thinking pictures are going to be next. Yeah, pictures are next. So be on the lookout for that. We'll try to figure out what's going on with all that stuff. But yeah, so this wraps up the money and the utility function model lecture. And now we're going to move on to a more general class of the real business cycle model. I might go through a little setup. I might explain some of the calculus and stuff like that. Really, there would only be one more first order condition you have to worry about, which would be for labor. And that will allow us to understand labor markets so we can draw pictures. But anyways, I'm probably just rambling. You're probably sick of hearing about this shit. You're probably ready to just have this video be done. So I'm going to go ahead and, well, recognize that fact and go, okay, well, this video is probably done. So this video is now done. And I hope you enjoyed the video. I really do. If you didn't, well, then that sucks. But anyways, that'll be that. So thank you for watching. I am glad, I'm sure you're also glad, that we're finally doing money stuff. We're doing money-related things. We're doing monetary policy, finally. And we're going to be able to do a little bit more cool stuff. And, well, by the end of this course, you'll actually have a really good understanding of how monetary policy interacts in the aggregate U.S. economy, and also how unconventional monetary policy interacts, because that's actually my specialty. So thanks for watching, and I will catch you next time.